So now we move to another important variable of landscape water balance, and that is soil moisture. And two dedicated satellite missions that are currently flying are the Soil Moisture Active and Passive Mission by NASA, SMAP, and the Soil Moisture Ocean Salinity SMOS mission, which is run by the European Space Agency. Between these two sensors or satellite systems, they give us global coverage multiple times a day of soil moisture status all around the globe. And our interest in this technology started over nearly 12 years ago, when my colleagues and I were part of a team to develop for the Bureau of Meteorology a new suite of water information products for the country. The question was whether satellite data were able to give insight to the distribution of water in the landscape better than what was then the current systems of just having the in situ gauges and the modelling. So this is all because the Bureau back in 2007 were, by act of law, mandated to collect and disseminate and manage Australian water resources from now on to the future, in addition to their meteorological monitoring programs. And so once water hits the ground, find out where it goes and what becomes of it, we had to develop the landscape water balance model. In this case, it's called the Australian Water Resources Assessment Model, AWRA, and it's the current way that we get Australia-wide information products about the water in the soils, water on the landscape, the runoffs in streams, the evapotranspiration from the land. It all comes to you via this model work that we were part of over 12 years ago. And so the question was, how can those satellite products, that soil moisture products, be used to better help predict the landscape water balance model? The details are not important, but do go have a look. There's a very good description of the processes at the water landscape website in the Bureau of Meteorology. So, as I mentioned, one way of satellite data by themselves are going to be gappy. They're not always exactly what we want, and in this case, the satellite technology only gives us what's up in the top few layers. And so we set upon trying to what's called assimilate these satellite data into the AWRA model. So data assimilation, broadly speaking, you start off with a model, a conceptual representation of the process that you're trying to model. In this case, it's a landscape water balance. We parameterize it, it's calibrated against past observations, just so that we can get the model system dynamics right. With that model, we make our first guess, a prediction of the system's states. These are the components of the model that dynamically evolve through time, like the water storages in the soil column, for example. And because those states aren't always what we observe, look, we observe, for example, runoff in the streams, but the system states are the soil water properties. So you have to develop model components that link the states to what you observe, and that's the observation operator. So then once you have the modeled equivalent of the observation you're trying to measure, you get an actual observation that's independent, part of the network. And as long as it's bias-free, we can assimilate those data, improve our model states through this analysis or state updating. And then we feed that improved state back into the conceptual model, and we have this loop going through. Human beings are natural data assimilators. So, for example, we walk along a path, and when we see an obstacle, we avoid it. Our trajectory will change to avoid collision with the obstacle. We can even change our opinions in light of new or compelling evidence. Well, that is, most of us can. Some politicians, maybe not. So, just another conceptual description of data assimilation. So we have the model states at some time, and because we want to represent its reliability or uncertainty, we represent it here by a discrete set of points. This is, if you like, the probability distribution or the range of certainty. The wider this oval, the less certain we are about the estimates. So here's an initial model estimate of the states at some time. We evolve the model forward to give us a forecast. And as the model evolves forward in time, you can see the error grows a bit, right? Then an observation comes along. Again, the oval here represents our faith in the observation. The smaller the circle, the more confident we are the observation is correct. The wider the oval, the less confident we are in the observation. So data assimilation takes the model estimate and the observation and comes up with a compromise. This is the analysis. It's the best combination of both the initial guess of the model and the observation to give us a revised system state. Then we evolve that forward in time to the next time step. Model growth, error growth leads to a spread of model estimates. Observation comes along. This time we're not so confident in this observation, so the model doesn't move too far away from its original guess when we come up with a compromise. We evolve that through time. This time we're super confident in the observation, so the analysis will move a lot closer to the observation. And then we evolve that through time. Maybe we don't have anything to assimilate at this time step, and so it just keeps evolving. So that, in a nutshell, is the process of data assimilation, coming up with the best trajectory of a model estimate given the observations that are available. So in the AWRA model, we set about trying to assimilate the satellite soil moisture products we had available. Now, at the time, there were two different systems, the AMSA-E and the ASCAT systems. The technologies have different pros and cons. Too much detail to go in at this point, but we felt it best to assimilate both these sources of information to give us best coverage over the continent and to give us best accuracy. So the question was, given this is a model representation of soil dynamics, the moisture dynamics in the soil of the AWRA model, and these are the observations we want to assimilate, the issue is that the satellite only really sees this bit of the model. So sorry, going back. So we had, the question is, by assimilating soil moisture that only really corresponds to this part of the model, does it help improve what's happening in the deeper soil column? And so we set about, we assimilated. There's a lot of detail here about the method of data assimilation. We employed this thing called the ensemble Kalman filter to give us this trajectory. Of course, it's applied over every pixel of the Australian continent. But what this shows is that where we have satellite observations to assimilate, there is a grey for not much change, to a blue, which means the assimilation adds water, or a red, which means the assimilation takes away water from the model. Where there's nothing, it means there was no change in the model state because there's no observation to assimilate. And what we see when we look at a time series is the initial guess, if you like, is in grey, and that by assimilating the observations, our model consistently moves towards the observations, which is what we want. But we don't want to move completely to the observation because we don't trust necessarily the observations wholeheartedly. There will always be an uncertainty associated with the observation. So we set about applying this en masse across the whole country, and then it comes down to evaluating the performance. And the take-home message of all that investigation was that even though the satellite only sees the top few centimetres of the soil column, by assimilating that data into the water balance model, we improve the root zone. The root zone is everything from 0 to 1 metre down in the soil profile, which is roughly across the country, is pretty much covers all vegetation types. And what this graph here shows, that for these in situ verification sites, those areas that had root zone moisture measurements, anything above the zero line here is an improvement at these stations in the performance. And so pretty much everywhere we got an improvement, and many of the sites were actually a statistically significant improvement. So We've since applied this concept to the assimilation of the newer sensors, the SMAP sensor I was talking about, for example, before. In the top here, we've got the global coverage of the satellite every day. So you can see many parts of the globe, this stripiness, satellite orbits mean that any one sensor doesn't exactly capture everything, but pretty good coverage nonetheless. We assimilate these observations into our water balance model, and the topsoil layer, the corresponding layer to the dynamic seen here, that gives us that full spatial coverage. But more importantly, like we have found repeatedly, going back, is that even though we improve the system topsoil layer, which is a good thing, the most important thing as far as agricultural production is concerned is what's happening in the root zone. So you can see this is the root zone moisture dynamics. It's a lot slower than the topsoil layer, not surprisingly. It's a deeper soil column. It takes a lot longer to wet up and dry down than the top few centimetres. So the dynamics is a lot slower in the root zone. Nevertheless, the message is consistent that by assimilating that satellite soil moisture information to our water balance model, yes, we improve the topsoil layer, but we also improve the root zone. And many studies my colleagues and I have looked at is consistently demonstrating this. And to be fair, we're not the only ones. This is a positive and consistent outcome of many studies by many authors around the world. So soil moisture is dramatically improved by assimilating it into water balance models, and it increases the utility. So we get the global coverage from satellite soil moisture. Actual soil moisture products will vary in their quality depending on which satellite sensor technology is used and which geographic location you're interested in. For example, SMAP works very well over areas of flat terrain. But as soon as you get into hilly areas, the more the systems called ASCAT perform better. There are active systems where the satellite sends a pulse of radiation down and measures the return signal. That does a better job at representing soil moisture in very hilly areas, for example. So satellite products together give us global coverage, but we try to combine the strengths of all the different sources of information, because we know any one system isn't perfect. But by combining them all, we tend to do better than any one alone. So it's like the same message with the rainfall work. Assimilation is an important feature here. By itself, the satellite soil moisture information is only is skin deep, if you like. It's the very uppermost layers of the soil column, at most 5 centimetres of the soil column. That's where the emissions from the ground are coming from. To make the most out of those observations, you have to assimilate that satellite observation into a water balance model, because that has been shown to give us better representation of the soil moisture dynamics in the soil states, and particularly improves the root zone moisture. And that root zone moisture will then be beneficial to farmers looking at where there may be deficiencies and where they might need to target sort of water resources, and also by linking the performance of linking root zone moisture dynamics to vegetation response, you can anticipate your sort of harvest or your yield predictions, how much biomass will be generated. But when assimilating soil moisture information, what you've got to do is, because you're changing the system states to better match the satellite observations, you've got to check that you're not ruining the performance in the model's estimates of other parts of the water balance. For example, the evapotranspiration or runoff. By improving the soil moisture, sometimes you find you're degrading the performance of runoff and evapotranspiration. That can point to a couple things. First of all, maybe the observations aren't so good. But another interpretation and what will require further investigation is perhaps there's an inconsistency in the model. Surely, if you improve the root zone moisture, you should improve evapotranspiration and runoff. So if you don't, then there's something wrong with the model and you need to revisit the model physics. So we covered a lot today and it was very quick and rushed. I'll start by saying that don't expect you to absorb much of what I said today, other than satellite observations can provide estimates of the key variables in the water cycle. Monitoring the water cycle is important. It's a key part of the Earth system that's connected with the carbon cycle, the nutrient cycle, and the photo production. And the atmosphere, of course, because how much moisture is in the soil will determine how much moisture gets in the atmosphere through evaporation processes and the like. So monitoring the components of the Earth system, particularly the water cycle, is important. It's important for water resource management because knowing where the water is and how much water there is important for water management, how much farmers get versus how much goes to the natural ecosystem. So for better understanding of how we estimate these variables, monitor these variables, we need the complete picture. And no single data source is enough. That's why we introduced this concept of model data fusion, because we do have sensor networks distributed across the country. They measure very precisely a single variable in a location on the landscape, but doesn't give you that complete coverage for, say, continental water resource management. Satellites, however, technology is up there on many platforms, giving us global coverage of precipitation information and soil moisture, for example. There's many more water variables I didn't go into, for example, evapotranspiration and groundwater runoff. These two can be estimated through satellite sensor technology. They're too much to go into in this very short amount of time. But the idea is satellite technology can provide estimates of key water cycle variables. Their quality, however, we don't know, because these are never direct measurements of the thing we're interested in. We always have to convert what the satellite measures into a quantity like rainfall, soil moisture, evapotranspiration, and that can introduce errors. And then, of course, we've got models as the way of giving us that full spatial, full temporal coverage of the water cycle variables of interest. But by themselves, they're kind of limited. And so through model data fusion and data assimilation, we can improve model predictions. I showed you the examples of fusing satellite rainfall information together to get that better spatial temporal coverage. So to the soil moisture data assimilation to the water balance model called AWRA to give us better representation of the root zone soil moisture. So that was a lot in a very short amount of time. Thank you for your patience and understanding. I think I hope some of you will be at least a little bit interested in pursuing this area of satellite sensing of the water cycle. Any questions about that, let me know. Very happy to field those. And yeah, thanks for your time, not just for this lecture, but all 6 lectures. Cheers.